Good evening, everyone. I welcome you all. Good evening, everyone. I welcome you all for the week 6 live interaction session for the course on Renewable Energy Engineering, Solar, Biomass, and Wind Energy System. Let's just wait for a few minutes for others to join before we begin our session for today. I hope I'm audible. So let me just share my screen. I hope my presentation is visible and I am also audible. So I welcome you all to the week 6 live interaction session for the course on Renewable Energy Engineering, Solar, Wind and Biomass Energy System. Myself Pratyumnan, I am a course team member for this course offered by Professor Vaibhav Vishant Gaut sir and Professor Anandan Lakshmi ma'am from the Department of Chemical Engineering, IIT Guwahati under the NPTEL program. So to start with our session today, previously in the last 5 sessions we dedicated our focus as well as efforts towards understanding how solar energy is a renewable source of energy. How can we harness energy from the solar radiation that we receive every day, from the sun that we see every day. We discussed on the fundamentals of the flat plate collector and the concentrating collectors which are used to concentrate the solar radiation falling onto the surface for our energy needs. And then we discussed over its geometric principle, the design principle, how to calculate the various parameters such as efficiency and the amount of energy that is actually taken up by the fluid in these collectors, and what is actually the fate of this heat taken up by the fluids in these collectors. So in the last 5 weeks we were able to actually have a good grasp honestly on what is solar energy, how we can harness the solar energy. From week 6 onwards we will primarily focus our attention towards using biomass as one of the renewable energy systems. So we will be discussing about the different types of biomass that is available, how these biomass can be used as a renewable energy resource, and what are its different properties, structures, and a lot more in the upcoming weeks. So before we actually move towards the biomass energy systems, we will discuss a few questions on the solar energy, which are nothing but your assignment questions. Some of you had actually raised queries in the last to last week, but unfortunately due to time constraint we were unable to take those questions for the in the live interaction session. So I hope by completing these questions and clarifying these doubts in this assignment discussion, we will be able to sum up the solar energy part in a proper fashion. So these are very basic questions which I feel it's actually important to discuss over here. So in case of the week 2 assignment discussion, if you see, the week 2 is something primarily focused on understanding about the amount of heat energy gained by the fluids. Specifically speaking, we worked on the design principles for the flat plate collectors. So we have 3 questions related to that today. Let's just check each one of them, and then we will be moving on towards week 3 assignment discussions. Over there we will be solving one problem again, so that you will be able to understand what kind of mistakes were done, because that question has been asked in the ask a question tab by quite a number of people. So yeah, so the question 1, as you can see here, I hope my PowerPoint presentation mode is visible to everybody. The first question is, which of the following materials is used as a anti-freezing agent to protect the flat plate collector piping system during the extreme winter season? So we have like 4 options, and if you remember, even in the week 2 or week 3 live interaction session, we specifically discussed what is the role of anti-freezing agent. So in extreme winter season, what actually happens is your water, so the main fluid that is used in this piping systems is usually water, and the reason why we use water is, apart from its easy availability, the volumetric heat capacity for water is the highest. So we can actually harness more amount of energy in a small volume. So that is the major reason of why we use water as a fluid for our both flat plate as well as the concentrating collector systems. So as everybody knows, water actually freezes at 0 degrees Celsius. So in case of extreme winter season, let's say specifically in the west part of the world, Europe or other United States, the temperature freezes below 0 degrees Celsius during the winter seasons, as well as in some other places also there are habitats where the temperature goes below minus 70 degrees Celsius also. So if you consider these kind of situation, over there using water as a fluid source for your in your piping system for the solar collectors may not be feasible and may not be wise, because the water will freeze. So once the water freezes, it won't have the ability to flow. So if it does not have the ability to flow, it won't be able to take up your heat and then go to the storage system. The heat won't be able to get transported from your solar collector system to your energy storage system. So due to this reason, we are supposed to add some kind of anti-freezing agent So one of these property of this anti-freezing agent is it actually prevents the freezing of your water at 0 degree Celsius. It will bring down your freezing point to up to minus 50 or minus 60 degrees Celsius, for example. So here we have four options. So if you see, black paint and ferric oxide, they are not used as an anti-freezing agent. They are primarily focused on applying these two components in the absorber plate. So black paint as well as the ferric oxide are used as a selective surfaces to actually concentrate the solar radiation that you get. So if you use these two, the amount of solar radiation that you will gain from the sun or whatever is falling, the concentration will increase, because black paint has the ability to actually absorb all the wavelengths of light and not release them back. So when it absorbs all the wavelengths of light, the dissipation of this, when it absorbs all the wavelengths of light, so the heat will increase. So the only option, and the iodine is used for other purpose in your flat plate collector, which we are not going to discuss here now. So the only option is your ethylene glycol. So we discussed this also in the previous session. So ethylene glycol, what it does is, when you add to your water in specific concentration ratios, it will actually bring down the freezing point of the water. So at a optimized concentration, when you add ethylene glycol to water, or even glycerol also can be used as an anti-freezing agent. If you add them to water, the temperature at which it freezes will lower down to approximately minus 50 or minus 60 degrees Celsius. So that can be used as, so when this ethylene glycol is mixed, then you can use the water or water ethylene glycol mixture as a fluid system for your flat plate collector piping, even in the extreme winter season. But one of the things we have to take care here is, when you add ethylene glycol to water and then you use it to transport your heat, once it actually reaches to your thermal energy storage system or other kind of energy storage system, you need to actually separate them. So that will again prompt us to use another kind of a separation system, where we actually have the ability to separate ethylene glycol and water. So adding ethylene glycol maybe is a good wise decision for extreme winter season, but at the same time you also need to install a particular system where you can separate both ethylene glycol as well as water. So the answer to this question is ethylene glycol. So the second question is, Boyer's law is used to calculate the transmissivity of the cover system of a solar collector based on what principle? So Boyer's law, if you remember, we use this mainly for absorption. So the transmissivity of the cover system that happens due to the absorption of the solar radiation. This is a straightforward question. If you remember, we also use this formula, Boyer's law formula, tau alpha equal to e power minus k delta r delta c by cos theta r, where k is nothing but is your extinction coefficient, theta r is the angle of refraction, as the solar radiation that gets incident onto your surface gets refracted, and your delta is nothing but the spacing between the covers. So reflection and refraction, you usually calculate the, yes, does anybody have any? Oh, it's not visible. Can you tell me which slide you? Yeah, which? Now we are able to see that week 2 assignment discussion slide. Or wait a minute. Now? Oh, okay, yeah. So I'll zoom it. So your emissivity will actually remain constant. The reflection and the refraction component you actually calculate using the tau r1 and tau r2, and the absorption of the solar radiation by your cover system you calculate using your Boyer's law. So the third question is Straightforward definition question. Heat removal factor, if you remember, the value of Fr is nothing but is the ratio of actual heat transfer to the maximum possible heat transfer through the collector plate. Yes, the answer is true. Now we move on towards our main discussion. So this is the week 3 assignment, and there were a lot of, I guess, queries raised over this particular questions. So the question states a flat plate collector is tilted at an angle of 30 degrees Celsius, located at a latitude of 20 degree north and longitude of 90 degree 30 minutes east, pointing due south. Calculate the following on 1st April for a non-leap year at 10 am IST by considering your monthly average hourly beam and diffusive radiation, that is your IV bar and ID bar. Those values are 1500 kilojoule per meter square hour and your ID is 900 kilojoule per meter square hour respectively. They have asked you to take the ground reflectivity value as 0.2. So here we will just like take this as a live solving session where I'll also be solving, and if you want, you guys can also solve parallelly with me and let me know if I'm going wrong anywhere. So okay. So here we are actually supposed to calculate the value of theta I and theta z. So cos theta z, if you remember, the formula is sin phi sin omega plus cos phi cos omega into cos delta. Yes, that is the formula. So let's just calculate now. So cos of theta z, or let me write cos of zenith, is equal to sin phi sin delta plus cos phi cos delta and cos omega. Cos phi is nothing but your latitude, that value is 20 and your beta value is 30, and the hour angle and the declination angle we are supposed to calculate. So first let us write that. So for 1st April, your declination angle will be 23.45 times sine of 360 into 284 plus n divided by 365. So that value will be, n value will be for April 1st, n value is so January has 31, and since it's a non-leap year, so February 28, March is again 31 and plus 1. So that is for April 1st. So the value will be 91. So your declination angle will be sine of, so 284 plus 91 into 360 divided by 365 and sine of this angle. So 284 plus 91 into 360 divided by 365, and sine of this angle will be this much, this into 23.45 is 4.016 in degrees. Now you have declination angle. Our angle, since it is our angle, so the value of our angle is 10 a.m. So 10 a.m. is in the morning, so it will be 10 minus 12 into 15. So if you solve parallelly with me, then it will be very useful, because this will be kind of a last session where we will actually take problems related to solar radiation or solar energy, because from now onwards we will be discussing majorly on biomass and wind energy systems. So that is 30 degrees, and here I am taking positive because it's in the morning. According to sign convention, if the time allotted to you is in the morning, you can take the value as positive. So 30 degrees. Then now you are good to calculate your cos of theta z. Cos of zenith I am writing here. That value is sine phi, that is sine 20, times sine of delta, that is 4.016, plus cos of 20 cos phi into cos of cos of delta, that is 4.016, into cos of your cos of 30, that is your hour angle. So the cos theta z value will be 0.837 So we know now cos of theta z, so we are supposed to calculate cos of theta I. So cos of incidence, that formula is sine of your declination angle multiplied by sine of phi minus b. So phi is your latitude, minus beta is your angle, is your slope, so that value is 30 degrees, plus cos of 4.016 cos delta times cos of our angle times cos of phi minus b. So phi value is 20 minus beta, that is 30. So this is your cos of theta I, or cos of incidence. So this value will be sine of 4.016 into sine of minus 10 plus cos of 4.016 multiplied by, so I am doing it here in my calculator, because the virtual calculator is not something feasible to actually write a bigger formula there, times cos of minus 10. So the value is 0.8386. So if you divide both, you will be getting your till factor for beam radiation. So that division I'll leave it to you because that's just dividing. So RB will be cos theta I by cos theta z, so 0.8386 divided by 0.8357, so that value will be 1.008. I hope the value is 1.00, it's coming approximately 1.089. I hope this is also the answer that is given in the key. This one is simple. So diffusive reflectivity is nothing but 1 minus cos beta by 2, so 1 minus cos of 30, that divided by 2, so which is nothing but 1 minus cos 30, so cos 30 will be root 3 by 2, 0.866 divided by 2, so that would be 1 minus 0.866 divided by 2. So this value you can calculate, and the similar for reflected radiations also. So let me move on towards, this is the place where the things becomes a bit more complicated. So let's start solving this one. So you are supposed to calculate angle of refraction, and all the other values are actually given, that is your number of cover, thickness of each cover, refractive index, extinction coefficient, and all the other stuff. So here again, so as we previously we start with the Snell's law, which is used for calculating the angle of refraction when your solar beam radiation fall onto your surface and it undergoes refraction because of the change in the medium of your light. So eta Ni, that is your refractive index of the incident medium, 1, sine of theta I, that is your angle of incidence, which is given as 30 degrees, that is equal to Nr, that is your refractive index of the medium where the light is getting refracted, which is your glass. So that is written as, given as 1.6 times sine of theta r, of theta r. So sine of refraction angle is equal to sine of 30 divided by 1.6. Sine 30 is half, divided by 1.6 will be 0.3125. And now you have to take the inverse to calculate the refraction angle. So refraction angle is equal to sine inverse of 0.3125. So that value will be 0.3125, and sine inverse of that 18.20. So your angle of refraction is, the answer is D. Now, so this part is clear now. Here you are asked to calculate your transmissivity based on reflection and refraction. So you are supposed to calculate the value of tau r. So in order to know your value of tau r, if you remember in the last week we had a flow sheet where we saw how to calculate the transmissivity due to reflection refraction component. First you are supposed to calculate the polarization components due to reflection and refraction, that is your rho 1 and rho 2. Once you get the value of rho 1 and rho 2, you are supposed to calculate tau r1, tau r2, tau r, that is nothing but tau r1 plus tau r2 by 2. So your rho 1 will be sine square theta r minus theta I, that is 18.2 minus 30 divided by sine square 18.2 plus 30. So the value will be sine square of minus 11.8 divided by sine square of 48.2. minus 11.8 sine of that value and square it up. 0.0418. That whole divided by sine square of 42.8. So that value will be 48.2.55. So if you divide both of this, then you will be getting your value as 0.075249. I specifically request everybody to take this value as such up to 5 or 6 decimal places, because this will have an effect over your answer what you are going to get. Similarly for rho 2, the value will be tan square of minus 11.8 divided by tan square of 48.2. So tan square of 11.8 minus 11.8 is 0.0436, and tan square of 48.2 is 1.250906. So that value will be 0.034889. So you now know the value of rho 1, rho 2, and since the number of glass covers given here is 1, so the formula will remain as tau r1 equal to 1 minus rho 1 by 1 plus rho 1. The value will be 1 minus rho 1, that is 0.075249 divided by 1 plus 0.075249. The value will be 0.860134. So I am repeating again, it is better to take the entire digit value, like up to 6 decimals. It is preferable, because when I solved myself personally, I found that this was a factor which was affecting from getting the exact answer what is there in your options. .860034. Similarly, tau r2. So tau r2 will be 1 minus rho 2. So 1 minus 0.034889 divided by 1 plus 0.034889. So that would be approximately 0.932574. 1 minus 0.034889 divided by 1 plus 0.034889, 0.932574. So if you take the average of two to calculate tau r, then the value will be 0.860034 plus 0.932574 the whole divided by 2. So the answer would be 0.8963. Let me just show that here. 0.860034 plus 0.932574 the whole divided by 2 is 0.8963. So your option B. Then we move on to calculate your transmissivity due to absorption and transmissivity absorptivity product based on beam radiation. So this is the formula. So tau alpha is e to the power minus k. K is your molar the glass extinction coefficient, so whose value is 10 times the delta C, that is your spacing between the cover, which is 3 millimeter. So we will take it in meters and then we will calculate. So 0.003 meters the whole divided by cos theta r, cos of refraction angle. So refraction angle is 18.20. The value would be, and since here we have only one glass cover system, we are not adding the extra term like 2 or 3. So those terms will come up as you increase the number of plates in your flat plate or your concentrating collector system. So 10 times of 0.003 the whole divided by 0.20, and cos of its value will be 0.9499. And the value would be here. No, sorry. So here we got minus 0.0315822 and minus, okay, let me just calculate here in my calculator. Minus 0.03 the whole divided by cos of 18.20. Point 0.031579. So 0.9, so let me just write it here, e to the power minus 0.031579, which is equal to 0.9869. That is option C. So then this is one of the questions which was asked in ask a question tab, where you are asked to actually calculate the transmissivity absorptivity product based on the beam radiation. Here this actually means tau alpha b and not transmissivity tau into alpha. So it's not tau alpha p. Transmissivity absorptivity product based on beam radiation is tau alpha of the entire beam radiation and not the transmissivity times the absorptivity of the plate. So let's just calculate this as well. This will be quite easy. So tau value is 0.8963. 0.8963. Alpha p, that is your absorptivity of the plate, is 0.95, and your diffusive reflectivity, here we take that value as 0.2, because if you remember, we discussed this previously also. Since the diffusive radiation gets scattered by the atmosphere, they will be traveling in all the different directions. So it is not possible to account for every single diffusive radiation that fall onto your flat plate collector, because each and every one of them will be at a different angle. So we take the value of theta as 60 degree and calculate. Similarly, for diffusive reflectivity, in these cases the rho d value we take it as 0.2 and then we solve for the system of this equation. So tau alpha of beam radiation is transmissivity 0.8963 times absorptivity of the plate the whole divided by 1 minus of absorptivity of the plate times diffusive reflectivity, which we take it as 2 here. So if you do this calculation, your value will be, this is tau r. We are supposed to calculate transmissivity, so that is transmissivity due to reflection refraction component times the transmissivity due to absorption. So 0.8963 times your 0.9689, whose value will be 0.8963 times 0.9689. 0.8963 times 0.9689, 0.8684. So this tau value is not tau, it is tau. Here the value of tau is tau r times tau alpha. Tau r times tau alpha. Here we have to take both the components due to reflection refraction as well as the absorption into consideration when you substitute the value of transmissivity. So it's 0.8684. So if you calculate this, it would be 0.8684 times 0.95, 0.82498, 0.82498, the whole divided by 1 minus 0.05 times 0.2. So let me just show the calculation here first. This value will be 0.8333. So which will be approximately 0.8335. So this is your answer. If you want, I can show here also. So 0.05 times 0.2, 0.01, yeah, 0.01, so 0.82498 divided by 1 minus 0.01, oh sorry 1 minus 0.01, 0.99, so 0.82498 divided by 0.99 will be 0.8333. So the answer is approximately coming around the same 0.8335. So this is the answer. So one of the reasons why for some of them the answer was not matching was probably either they would have did the same mistake which we committed here just by taking the value of tau as tau r and not calculating the product of tau r tau alpha, or it could be probably because since they have asked transmissivity absorptivity product, there are chances that there can be error by just multiplying the tau as well as the absorptivity component, that is your transmissivity absorptivity component. So this is the procedure to calculate the transmissivity absorptivity product based on beam radiation. So here we have solved for all the entire set of questions that you have for week 3 assignment. So in case if you have any doubts, then feel free to ask to me now. Oh wait, let me just check. So if you guys have any doubt, then please do let me know. And also let me know like whether was your answer actually matching with the answer in the answer key which was given to you in the portal. So if your answer was matching, then since our answer is matching now after solving, so it's just that we came to know that we have to be specifically focused on calculating all the parameters very precisely. So it's not just that we take only 2 or 3 decimal places, since each and every value is having 4 decimal places and their values, the difference between each value in the option is also almost, the difference is negligible or like very small. So it's better we take up to 5 or 6 decimal places and then calculate all these parameters such as your transmissivity due to reflection, refraction, absorption and their product. So you need to be precise when you are calculating these parameters. So if you do that, then all your answers like how we did here, they will match with your options almost exactly. The answers will be very precise. So now we are done with this. So let's just move towards, okay, we have one more question. This is a very simple question. So they are asking you to calculate the net present value of a solar technology project. Everything is straightforward. You have your net positive annuity, that is nothing but your yearly savings due to the use of your solar technology. So you're going to use solar technology, so through which you are going to actually derive energy. So how much is the amount of savings that you can do by installing the system? So per year it is around 32 lakhs, like that you are going to do for 20 years, and your salvage value, that is some kind of a compensation, will be around 6 lakhs. And then the initial cost of the project, that is the initial cost of setting up of the solar technology project, is 3 crore 20 lakhs. So the net present value is calculated using this formula, minus initial cost plus S. S is nothing but your number of years for which you are actually going to use the system, or like if you are going to think that this will be there for like for a long term, how much years will you be able to use this solar technology or the kind of setup that you are going to install. Annuity, as I said, is nothing but your yearly savings of how much you are going to save by using this solar technology project, and your salvage value. So if you calculate this, the answer is coming around 3 crore 26 lakhs, And in the option, since they have asked to you, since they have specifically mentioned in the question that you are supposed to present your values in terms of crores, so it's come 3 crore 26 lakhs or nothing but 3.26 crores. So the options are actually given in terms of crores, so the net present value should be 3.26. So the correct option is 3.26. Yeah. So yes, now we have come to an end with our solar energy as a renewable energy system. We move on towards our next energy source, that is nothing but your biomass. In our course, we are specifically focusing on biomass as well as wind energy and solar energy. So the biomass here, we consider it as an energy source. In the very first lecture, when we discussed about what are the characteristics of renewable energy, there was a question raised in the discussion chat box, like asking why a biomass need to be a greener energy resource. Like one of the characteristics of for renewable energy is that it should be cleaner and greener, so that it does not pollute the environment. So there was a specific question on how come you are saying that you burn the biomass. So when you burn the biomass, you are obviously going to release pollutants and other carbon compounds into the atmosphere. So how do you actually say biomass is a greener energy resource? So we will discuss about this in detail today. So if you see these plants, what you get, they actually nothing but they take up this carbon dioxide from the atmosphere and then convert it into glucose or carbohydrates and then store it in them. So the biomass for this kind of plants is actually obtained from the carbon dioxide that is present in the atmosphere through a process called photosynthesis. So the photosynthesis process is nothing but the carbon dioxide as well as the water molecules from the environment is taken up by the plants and then is taken up by the chlorophyll present in the plants, and then both these carbon dioxide as well as the water undergo a reaction in the presence of sunlight. The reason why we require sunlight is because the sunlight helps in the photolysis of water. By photolysis, what I mean is the splitting up of water into hydrogen as well as the hydroxyl group, and they react with this carbon dioxide in the chlorophyll system. It undergoes a complex process, and then what we obtain is the carbon dioxide, and then the oxygen comes out. What we obtain is the carbohydrate or glucose in its simplest form, and the oxygen is released out. So this glucose is nothing but is actually stored in the plants. So this actually forms or creates a kind of is what is the biomass for the plants. So now when these plants are going to die, or when you use these plants to actually burn, when you use these plants and burn them, so you are going to release carbon dioxide. The carbohydrates which was actually synthesized, you use oxygen because for burning oxygen is required. So this carbohydrates and then the oxygen are burnt at an increasing temperature, resulting in the formation of carbon dioxide. So whatever the amount of carbon dioxide that you intake during the photosynthesis process for making the food, or what you call it as biomass, is what is going to get released into your atmosphere when you are going to burn this material or the plants. So the amount of carbon dioxide what these plants intake and what is going to get out by burning them is the same. So the net amount, if you see in the environment as a whole, the net amount will be same. So there will be a carbon neutrality or carbon dioxide neutrality. The amount of carbon dioxide that is present in the atmosphere will almost remain the same. But when you burn these biomass, you are actually going to extract some energy. So that is why we say a biomass is nothing but is a greener energy resource. we take energy, but at the same time we also make sure that the amount of pollutants that it generates to the environment is actually less. So that is the reason we have written it. We are specifically saying that the net carbon footprint, the amount of carbon dioxide or the carbon in the atmosphere, will be 0. That is, there will be no any net difference in the amount of carbon dioxide that will be present in the environment, but at the same time you actually use the energy, get these energy from the biomass. So that's why it is called as the greener energy resource. And since these plants and animal, whatever we classify as a biomass, is going to remain in the ecosystem for a long period of time, like throughout the existence of the humanity, there is no existence for these plants and animals. So there is no fear of them getting depleted. They are always going to be present. So that is the reason why we call it as renewable energy. So the biomass as such, there is a particular classification of what you can actually include as a biomass and what you cannot. So according to the standard definition, any kind of plant or animal waste, or any kind of a botanical plant species or biological animal waste sources that are non fossilized, that is, it is not something that is there for thousands of years, which has undergone degradation, and then you, due to high pressure and temperature, and you extract them from the earth. These are something that is living at present in the moment. So something that gets fossilized due to, during the millions of years, due to millions of years of process, and then upon this temperature and the pressure, upon high temperature and the pressure, that is what is called fossil fuels. Biomass is something that is going to be in the present times at the moment, like right at the moment. So that is why it is specifically mentioned even in the definition that the biomass should be non-fossilized fuels. That is, they remain at the present moment and not something that has undergone degradation or processing under high temperature and pressure throughout millions of years. So if you see, that's what is written. Biomass includes only living and recently dead biological species that can be used as a fuel or in chemical production. So it's not necessary that always you take these biomass and burn them and then get these energies out of them by burning them. Sometimes we can also process these biomass or the feedstocks that is available into fuels like bioethanol, biopropanol, and other kind of biobutanol. These are kind of the energy fuels which will be useful for some other applications. So they can also be used in case of the chemical production like biofuels, bio oils. So those oils can be used in many places. For example, it can also be used in the automobile industries and some other industries where the use of oil is more. So over there we can use them. So biomass need not always be burnt up and then their energy has to be extracted, but they can also be converted to other chemicals and the fuels, and from there you can synthesize the energy or you can use it. So that's what it can be used as a fuel or in some other chemical productions like bioethanol, biobutanol, and you can use them for varieties of application, and bio oil, which you can use it for your automobile or some other industry areas where this oil is required in huge quantities. And it comes from botanical and plant waste or a combination of these two. So biomass are of a variety of different types. If you see, you have your you have your primary feedstocks as well as that of the secondary feedstocks, and then upon that you have different classifications. You can actually extract biomass through your plant cell and cell walls. In these plants you can use them as an energy uh, stocks for your energy crops. yeah uh, yeah you can use these. You can classify the biomass as primary feedstocks and secondary feedstocks, and then you have these energy crops in their classification, which you can actually use them either for burning or, as such as I said, for some other fuel production. So these biomass, if you see, you have to characterize this biomass. So there are two types of characterization, or like kind of an analysis of the biomass. One is the proximate analysis, and another one what you have is called as the ultimate analysis. Proximate analysis is something that is mainly or primarily focused towards understanding the physical physical components in the biomass, like your percentage of fixed carbon, the ash percentage, how much amount of volatility is present, the bulk density, something that is specifically focused on the physical properties of the biomass. Whereas if you see in case of ultimate analysis, those are something that is with the chemical composition of your biomass, that is how much percentage is your carbon in the biomass, what is the percentage of hydrogen, oxygen, or does your biomass have any other kind of impurities that is present in them. So these chemical composition and their analysis comes under the ultimate analysis, whereas your proximate analysis is something that is focused on your physical parameters such as bulk density, apparent density, true density, what is the volume of the voids that is present in the biomass, how much is the percentage of moisture, and how much is the percentage of the volatile components that is present in your biomass, the fixed carbon percentage, the ash percentage. All those things comes under your proximate analysis. So there are varieties of ways to have a understanding about both these proximate as well as the ultimate analysis. In case of the proximate analysis, since it's more towards understanding of the physical properties of the biomass, one of the ways to calculate what is the percentage of volatile components present in your biomass, or what is the percentage of moisture present in your biomass, we go for the TGA technique. So TGA technique, does anybody have an idea of what is TGA and what is TGA actually? It's a kind of a thermal technique, thermal characterization technique, which we use for these biomass application. Majority of the biomass for the TGA is a specialized technique for biomass characterization. For any kind of biomass, if you see the literature, you can actually see the TGA as well as DTG plots, and then you can see their analysis about the proximate and then you can see their proximate analysis, what is the percentage of volatile components present in them, and then the fixed carbon percentage, ash percentage. So the TGA is one of the important characterization techniques for these biomass components. So does anybody have an idea of what is the TGA, like what is the full form of TGA technique, TGA characterization technique? Yes. Does anybody have any kind of idea of what is TGA? So So TGA is nothing but thermogravimetric analysis. This is a kind of a characterization technique where we understand about how does the material degrade under different thermal environments. So let me, oh sorry. So if you see here, this is the TG percentage, that is your weight loss percentage, and then your x-axis is the temperature. So the TGA thermogravimetric analysis technique is something where you actually learn about your material's thermal degradation pattern by raising its temperature. So you have a TGA machine, so and then you load your sample. This techniques usually use mass between 5 milligrams to 15 milligrams of sample, very little amount of sample, and then you keep it in a pan and then you heat the sample. So this heating is something which is done in an inert atmosphere. So we pass actually nitrogen gas or some other kind of gas like argon gas, helium gas, or krypton gas also. But one of the disadvantages while moving with these noble gases is that the cost, they are very expensive. So majority of the TGA characterization technique is done in the nitrogen gas atmosphere. Why we actually don't do it, these kind of characterization techniques in the oxygen atmosphere, is because your biomass is a carbon based components. So unless or until you want to study something related to your combustion process, you don't want to use oxygen, because when you increase the temperature and when the oxygen molecules are present, and if majority of your sample is going to be carbon based sample, so the chances of the carbon reacting with the oxygen to form the carbon dioxide is more. So in those cases, if you see here, your graph actually falls with the temperature. That means the mass of your substance of what you loaded, that 5 or 15 mg whatever you have loaded, is getting lost, is going down. The mass value is decreasing as we increase the temperature. Suppose if you use oxygen environment, and if your material, let's say some kind of a biomass you take, that reacts with the oxygen, it will result in the formation of carbon dioxide or carbon monoxide. So that depends upon the particular component and how much oxygen is required. If you have sufficient amount of stoichiometric quantity of oxygen present, then you will have the formation of carbon dioxide, which will be majorly the case. So in those cases, what you can see is, instead of this graph falling down, the graph will start to increase. The mass of your the mass that you loaded in the sample, if you observe those kind of curves, you can see that the percentage of the mass will increase instead of falling. If you see my arrow mark, you will be able to understand the curve will start rising upwards. So you want to avoid those, because then you will not be able to characterize your material or know what is the percentage of volatile matter present in your material. So that is specifically the reason why we use the nitrogen gas atmosphere. And we vary the temperature between 0 to 1000 or 1100 degrees Celsius, or if you want to keep it to a lower extent, you can also go up to 800 or 600 degrees Celsius. So that depends upon the biomass, and or in general that depends upon your material and its degradation behavior in the thermal environment. And this temperature increase, we do it at a particular ramp rate, which is nothing but a heating rate, that is how much you increase your temperature in 1 minute, like 10 degrees Celsius per minute or 20 degrees Celsius per minute. In majority of the cases, the ramp rate or the heating rate will not be a major concern. It will be almost the same, your thermal degradation pattern. But sometimes in some cases, if you see, there will be changes. There are literature which actually report a very minimal amount of change due to the change in the ramp rate of change in the heating rate of your of your sample. So if you see here, the first degradation that happens up to 100 degrees Celsius, or here in case it's if I'm not wrong, it will be approximately 70-75. There will be a first degradation. The curve starts from 25, so you actually start this analysis of your sample at 25 degrees Celsius. So you start increasing the temperature from 25 degrees Celsius. So if you see here, up to 200 degrees Celsius, whatever the amount of mass is lost is nothing but is due to your moisture, because if you see, the moisture is nothing but it's the water molecules that is present in your material. So majority of the water molecules will disappear at 100 degrees Celsius, like will turn it into vapors and then gets vaporized at 100 degrees Celsius. But that is something more towards the case of your free moisture. What is a free moisture is nothing but, let's say you have a material, whatever the moisture that actually surrounds your material, this moisture that is surrounding the core of your surrounding your material is the free moisture. But there is also something called as a bound moisture, which is actually bound inside your material. So those moisture has also to be removed. So that is the reason we increase the temperature, and the very first place where your moisture actually, where your curve actually starts falling, that difference is what we designate as moisture content. After that, if you see, there is a steep degradation of the material. From approximately, the mass loss is from 90% to 20%. So such a steep loss over a very narrow range of temperature, or like over 100 or 200 degree, over a small range of temperature, this particular fraction is what we designate towards the loss of the volatile components. So those components that can be readily removed or like gets vaporized upon the application of a very low temperature up to 400 degrees Celsius. So this is something, this weight degradation pattern is what we assign to a volatile matter. And then as you keep increasing your temperature, you see that there is after a particular temperature, you do not have any mass loss happening in your system. So that percentage where your degradation curve almost remains constant with respect to temperature, that amount of component is due to your ash content that is present in your material. So ash content, or the content which cannot undergo degradation even at those temperatures. So the ash content is something that is inorganic components. Mainly the inorganic components is what we classify as ash. So inorganic components usually don't degrade with respect to temperatures like 900 or 1000 degrees Celsius. So they require even temperatures beyond 1000 or 2000 degrees Celsius also. So this particular, the very small fraction of the mass left in your pan is due to your the ash percentage in your biomass sample. But since your biomass is nothing but it's a very complex compound which has multiple components, like if you see, mainly in case of the crops or the plant based biomass, you have your cellulose, hemicellulose, pectin and lignin. And cellulose and hemicellulose, if you see here, their degradation pattern cannot be distinguished, like both of the degradation happens at a very close temperature, so you cannot distinguish them in this TGA curve. For that reason, we go for the DTG plot, that is called differential thermogravimetric plot. So here you can easily visualize what is the amount of degradation that is due to your hemicellulose content, which is this one, and then this one is to your how much amount of the degradation happens at this temperature due to the cellulose. Oh yeah, actually sorry, my system just got hanged, so I just relogged in. So we were discussing about, am I audible? Anybody? Am I audible to you all? Okay. So if you see, this is what is called T offset and this is T onset. So T onset is the temperature at which the decomposition starts, and offset is the temperature at which the decomposition ends. And then the peak decomposition, if you see, at what point of time or at what point of temperature does my material undergo a maximum decomposition. So that is evaluated by taking a midpoint between this T onset and T offset, that is T peak. These two curves over here represent for the degradation that happens due to your hemicellulose as well as cellulose content. So since we are discussing here about cotton, so cotton has both cellulose and hemicellulose content. So this one, the peak that is more sharper is due to your hemicellulose, and then the other peak is due to your cellulose content. So the DTG plots, one of its advantages is that if there are multiple components which are undergoing degradation in your material or in a particular temperature, and you cannot actually distinguish them, because if you see between 200 to 500 or 600, it's just a steep line, but within this temperature range, both your cellulose and hemicellulose content is undergoing thermal degradation, but they are not visible. So in that case, a DTG plot will help us to understand how much, what is actually the percentage of your hemicellulose that is going to undergo degradation and your cellulose content that is going to undergo degradation. So this is one of the kind of advantages for a DTG plot. Both this DTG and the TGA plot will come simultaneously, so it will be easy for the analysis. And this TGA is not just used in case of the biomass, even though one of the major characterization of biomass is the TGA, but even for others materials like metal, like any kind of carbon based material, polymers, we do this TGA plot in order to understand the thermal degradation pattern of how the particular material is going to degrade under different temperature conditions. So this TGA is one of the many characterizations that we do in the while characterizing the materials that we use for different applications. So let's move on towards solving the questions that is specifically for this week. These 4 or 5 questions that we are going to discuss now will be extremely very helpful for solving your assignment questions, because that's how the model of the questions are. So it will be easy for you to solve your assignment questions. So the question, there are 2 parts to a question, so let's go part by part. The first part is that your weight fraction of moisture content in a biomass sample on a dry basis, that is nothing but M dry, that is what you are supposed to calculate. So calculate this one, that is your dry basis moisture content, and then they are asking us to take the value, that is your weight of biomass before moisture removal as 8.45 grams, and then the moisture removal after as 7.68 grams. So your moisture content on dry basis M dry is given by this formula. M dry is nothing but weight of your biomass sample when it is wet minus weight of your biomass sample when it is dry divided by your weight of biomass material when it is dry. In case if it is a dry basis, the denominator what you would be using is the weight of the biomass sample with respect to the dry component that we are using. If it is on wet basis, that means the basis on which you are calculating your moisture of the percentage of moisture in your sample is based on the wet conditions at is based on the wet conditions. So in that case your m wet will become weight of the biomass when it is in the wet condition minus weight of the biomass or the material when it is under the dry condition with respect to your weight of the biomass that is in the wet condition. So since the first sub question is on the basis of calculation of the weight fraction of the moisture content on a dry basis, so here our denominator is dry and the moisture content is how much amount of the moisture is there in my sample. So if you calculate your sample plus the amount of moisture, if you know that weight and if you know the weight of your component, so it's just the simple difference will give you the weight of the moisture that is present in the sample. So before moisture removal is what we call it as a wet component, that is 8.45 grams as given in the question, and what is after moisture removal is what is your dry component, because once you remove all the moisture from the sample, what you obtain is your dry biomass, that is 7.68. So since this is on the basis of dry weight, so here we take weight as weight of the biomass sample in dry condition, so that is again 7.68. so if you do the calculation, so it's a very simple calculation, so 8.45 minus 7.68 divided by 8.45, oh sorry 7.68, because here it is in the dry basis condition, 0.100, that's what we have got here. Suppose if the question asks you to calculate on wet basis, then you are supposed to, the numerator remains the same, that is before moisture removal and after drying, this the amount of moisture will be the same, but the weight fraction on what basis you take will be different. So here since it's a wet basis, we divide it by 8.45, that is 0.0911. That is what is given here. M wet is the moisture content, that is nothing but your weight fraction in wet basis. Let us just write here that also. So the W wet minus your W dry is the moisture, is the weight of moisture, and here we are asked to calculate the weight fraction, so we divide that weight of moisture either with respect to the weight of your biomass sample in wet condition or weight of your biomass sample in dry condition, depending upon the question and what they are asking us to keep as the base. And if in case if they ask only to calculate the amount of moisture, then it is nothing but weight of the wet biomass sample minus weight of the dry biomass sample. So this is 0.99. So let's check the second subdivision. You are asked to calculate the weight fraction of moisture content in a biomass sample on a wet basis, but here instead of giving you the weight of biomass before and after moisture removal, they have given you the moisture content, and that also in the weight fraction for dry basis as 0.47. So that means if you see here, moisture content on dry basis is 0.47 m dry, and this is a weight fraction which is given to you directly. So m dry and its weight fraction is 0.47. Now we have to calculate the weight fraction of the moisture content in the biomass sample on wet basis, so m wet. So m dry is nothing but 1 minus m wet divided by m wet. So if you do the cross, if you express m wet in terms of m dry, so m wet will be equal to 1 by 1 plus m dry, and that is nothing but 1 by m dry is 0.47, So your M wet, or the weight fraction of the moisture content in your sample on the wet basis, is 1 divided by 1.47, that is 0.68. 0.68. Suppose if you are if you want to know like how you are giving this formula, M dry is nothing but 1 minus M wet divided by M wet, you can actually substitute their expressions, and then if you see, both will be the same. So if you take M dry, let's just see for the RHS term, 1 minus M wet divided by M wet. So 1 minus M wet, that is weight of your, let me keep it as moisture for simplicity, divided by weight of your wet sample. So that the whole divided by your M wet. M wet is M moisture divided by W wet. If you do this, if you take this to the other side, so weight of wet divided by your W wet will be nothing but weight of dry, and then if you solve this, you will be getting weight moisture this is nothing but your M dry. So here also similarly, if you know what is M wet, then you can calculate M dry very easily. So if you know M wet, let's say they gave your M wet value as 0.53 or 0.53, then you can subtract 1 minus 0.53 divided by 0.53, that will give your M dry. Let's proceed to the next question. So I don't think anybody will have any doubt in that last question, because that was not a very difficult one. It's just that you need to know the formula and then just substitute the values there, that's all. So if anybody has any doubt on the conceptual basis, or any kind of if you are not able to understand what is wrong, or wherever if you don't understand, then please do let me know. Yes, okay. So in case if nobody has doubt, then let's proceed to the next question. So here we take a biomass sample of mass 8.95 milligram, that is on a wet basis. So here your mass is having even the moisture within them. Now you say that, now it is written that the biomass sample is heated to remove the moisture. Now you assume that 25% of the sample 25% of the weight of the sample is lost as moisture upon drying of the biomass sample. Then the bone dry sample is burned to 800 degrees Celsius to derive energy from the biomass. The ash is recovered after burning and its weight was measured as 2.53 grams. Now calculate the percentage of the ash based on your moisture free sample. So you can actually try this out. This is a very simple question. So here it is written 25% of the weight of your sample is going to get lost as moisture upon drying. So you have 8.95 milligram of your sample as the total weight, that is your weight of your sample plus the moisture, everything within them. 25% is going to go out. So 25% of that 8.95, and then you subtract that from 8.95, so you get your weight of the dry biomass sample. Now you are going to take this dry biomass sample and you are going to burn at 800 degrees Celsius so that you can actually get energy from them. Yeah, once you start burning, they will give you energy. So you are going to burn it to 800 degrees Celsius. Now you are actually recovering the ash. So once you burn it to 800 degrees Celsius, almost all the kind of carbon based components will be lost from the biomass. Whatever that will be remaining to you is nothing but is the ash. You are going to recover the ash and then cool the ash down to your normal room temperature, and then you are going to measure the weight of the biomass sample, weight of the ash that is left in the biomass. So that comes around 2.53 grams. Now you have to calculate the percentage of the ash based on moisture free sample. So that is nothing but, so since we know how much amount of the weight, how much amount of your ash is going to be present in the sample, and that is clearly given as 2.53 mg directly, and only you need to calculate your, so you have a biomass and then you want to calculate how much percentage of the ash is present in it. So that is nothing but weight of the ash divided by weight of your biomass sample into 100. That is, it's just how much amount is going to be present in that component. That's all. That calculation is ends there. So if you see, weight of the sample after drying is nothing but weight of your wet sample minus the weight of moisture, and 25% of your sample is nothing but is moisture only. So moisture content is nothing but 25 by 100 into weight of your sample. 25 by 100 into 8.95 is 2.2375, and weight of the sample after drying will be 8.95 minus the moisture content 2.2375. Oh, sorry, there was a network issue, so let me just present. Yeah, So here we were, so percentage of your ash is nothing but weight of your ash divided by your weight of the oven dry sample. So which is nothing but 2.53 divided by 6.7125, which is your weight of the bone dry sample into 100. Now, so here the next question is, consider a biomass sample of sugarcane bagasse. Okay, sugarcane bagasse is also one of the kind of a byproduct that you will obtain after processing the sugar. So if you take a sugarcane in a let's say in a sugar factory or a sugar industry which actually manufactures sugar, they take the sugarcane, process it, and then the byproducts that gets generated is nothing but the bagasse and the molasses. So here we take the biomass sample of a sugarcane bagasse, and the water, that is your the percentage of your moisture, percentage hydrogen, and then the HHV, higher heating value, is given as 16.5%, 20% and 17,120 kilojoule per kg. They are asking you to calculate the lower heat value of your fuel, and then the latent heat of vaporization is given as 2250 kilojoule per kg. So the formula that you are going to use for this is LHV is nothing but equal to HHV minus, that is your lower heating value, equal to higher heating value minus latent heat of vaporization times 9H minus M divided by 100. H over here is nothing but your percentage of hydrogen present in the sample. M is nothing but your percentage of moisture present in the sample. So HHV is given, that is 17,120, and your latent heat of vaporization of water is given as 2250, and both are in the same units, kilojoule per kg. So H is 16.5. Here we take specifically only 16.5 and not 0.165 or 0.2 for moisture, because we are dividing already the formula by 100. So we don't actually convert them into proper fractions and then we just take their absolute value, because 100 is already included in the formula. So here we take H as 16.5 and then M as 20. So if you do the calculation, your value is going to come around 14,228.75 kilojoule per kg. So it's just a simple mathematics. So you will be able to get this value. Then we move on to the next question, and this will be the final question for our live interaction session for today. The question states that determine the percentage of the fixed carbon of a biomass sample on both the wet as well as the dry basis. You are asked to calculate the fixed carbon percentage. They have given the weight of a crucible as 4.5 grams, and then your difference in the initial and the final weight of biomass, that is final weight of biomass minus your initial weight of biomass, is your 0.2 grams, and then the initial weight of biomass plus crucible comes as 8.15 grams. So the volatile matter and the ash percentage are given as 21.75 and 9.5 respectively. So how do you calculate the moisture content present in the sample? The formula is Wi minus Wf divided by Wi minus Wc into 100. Wi is your weight of the initial or the initial weight, Wf is your final weight of the biomass, and then Wc is your weight of the crucible. So you cannot actually since you cannot measure the sample without a container, you actually have to place the material in a container to measure. So we have to take the difference of your weight of your sample plus crucible minus weight of your empty crucible. So weight of the crucible is 4.5, weight of your biomass plus crucible is 8.15 gram. So and then it is given Wi, that is your initial and final weight of biomass after moisture removal, Wi and Wf, their difference is given as 0.2 grams, and Wc, weight of your crucible, is given as 4.5 grams, and the initial weight of biomass plus crucible is given as 8.15 grams. So Wi over here is weight of mass plus crucible, that is 8.15. To get the initial weight of your biomass, it will be 8.15 minus 4.5, and since the difference is also already given to you as such as the data, Wi minus Wf will be 0.2. So 0.2 divided by 8.15 minus 4.5 into 100 will be your moisture percentage. If you calculate 8.15 minus 4.5, the value will be around 3.65. 0.2 divided by 3.65 will be 0.05479. That into 100 will be 5.47 percentage. So the moisture content that is present in your sample is 5.47 percentage. But we are asked to calculate the fixed carbon percentage of our sample. So how do you calculate the percentage of fixed carbon in our sample? So if it is dry basis, then the percentage of fixed carbon is something that you calculate without the moisture, because the moisture has already been removed from the sample. So that is 100% minus volatile plus ash. So the fixed carbon is what is the carbon that is present in the sample apart from the contribution from the volatile and the ash component, because ash component is your inorganic component and volatile component will go away, will go away when you heat the sample. So it's 100 minus percentage volatile plus percentage ash. Percentage volatile is given as 21.75 percentage and percentage ash is given as 9.5. 100 minus 21.75 plus 9.5 will be 100 minus this value is 31.25. So fixed carbon in case of the dry weight basis, the value will be 68.75 percentage. And in case of the wet basis, if you are supposed to calculate, then in case of the wet sample, you will have to also include your moisture content. So that is, in that case, your formula will be 100 minus percentage volatile plus percentage ash plus percentage of your moisture content. So moisture content percentage we calculated as 5.47. Volatile matter and ash is given as 21.75 plus 9.5 percentage. So your total will be 100 minus 21.75 plus 9.5 plus 5.47. It will be 63.28%. So on the basis of dry basis you get 68.75 and wet basis you get 63.28 percentage. So this is what will happen in case of your biomass. So you have to be careful in taking the basis, on what basis are they asking you to calculate your percentage of moisture or percentage of volatile matter or percentage of the ash. It can be either on the wet basis. In case if they ask you for the wet basis, you are supposed to take the weight of the biomass sample before drying or the sample which has a moisture content in it. If the question is asked towards find the percentage of fixed carbon or whatever or in dry basis, then you are supposed to take weight of your biomass sample dry, that is the dried weight of your biomass sample. So this you have to be particularly be very careful on what is your basis, whether it is a dry basis or wet basis. And apart from that is your yes, apart from that, this for this particular week we do not have anything else to cover. We have covered about DTGA, DTG plot, the different kind of analysis, why biomass is a greener energy resource, and what is the specific definition, like what components you can classify as a biomass. Then in the solar part we calculated how to calculate the net present value. We saw how to calculate your net present value, and then the transmissivity questions which was given in the assignments. So now please feel free to ask if you have any questions. So I'll be here, you can always ask, you can ask me any questions if you have. Yes, does anybody have any questions with respect to today's live interaction or any kind of questions related to the solar energy systems module? Then please feel free to ask. Either you can unmute your mic and ask, or you can drop your questions on the chat box. With these three questions, like with these 4 or 5 questions that we have solved for biomass today, you will be able to comfortably solve your assignment questions for the week 6, which is probably, I guess, due within another 1 or 2 days. So let me, I hope if there are no questions, then let me just stop presenting. So in case if you have any questions, then do let me know now, or you can always type it in the chat box, or please unmute your mic, or you can also email me. My email ID will be given in the presentation that you can access. If you go to the NPTEL portal, in the left side, in the left hand side of the course page, at the bottommost at the bottom you can actually find the session the problem solving session option. If you go there, then you will be directed to a Microsoft Excel sheet from where you can access the PowerPoint presentation as well as the video lectures. If you have any doubts, then please feel free to email me and I'll be able to help you out very soon. So in case if you don't have any questions, then I would like to conclude today's session here. So I thank everybody for joining today in this Sunday afternoon. So thank you all for joining today's week 6 live interaction session for the course Renewable Energy Engineering, Solar, Wind and Biomass Energy System. We will have our next live interaction session on 10th of March, same time from 5 p.m. to 7 p.m., where we will be discussing more on how biomass can be used as an energy resource. So I hope to meet you all in the upcoming weeks as well. And I also take this as an opportunity to thank both Professor Vaibhav Vishant Gaut sir and Professor Ananda Lakshmi ma'am for giving this opportunity to interact with you all in a Sunday afternoon in a platform like this, as well as to the NPTEL team. I extend my thanks for their support, and so hope this live interaction session has been helpful for you. And yeah, so bye and meet you all next week.